just in case. Okay, so we're still in discussing ideal flows. Again, those are irrotational, incompressible flows where the velocity derives from the potential, and that potential is a solution of the Laplace equation. So I think last week and the week before, we discussed ideal flows in the 2D planar geometry. And now we are discussing ideal flows in sort of a 3D geometry, but really it's an axisymmetric geometry. So you have to think about the flow around a sphere or the flow around an elongated body, any sort of geometry or object that has an axis of symmetry. That would be the flow around, that's the kind of flow that we are representing. So we derived all of the different potentials and stream functions for the similar sort of building blocks of what we did for 2D planar flows, so uniform flows, sources, sink, and dipoles. We also discussed that in the case of 3D axisymmetric flow, you don't really expect a vortex because like any sort of singularity or building blocks that would generate a circulation would not be an axisymmetric flow. So you would be out of the axisymmetry assumption. And so the example we're going to do is to derive the flow around a sphere. And as you will expect, it's going to be very similar to what we did in 2D planar geometries. So that is point 4, flow around a sphere. So this is the easiest flow, axisymmetric potential flow, I should say, that you could derive. So this is simple axisymmetric potential flow. There are more potential flows in the book. So, and there are examples with the full derivation. So if you go into section 5.7 of your book, 7 point something. I forgot my book again, so I can tell you. But you'll see that there is an expression given, like a full derivation given for a much more complex flow, which is axisymmetric, sort of an object which looks round in the front and sort of pointy to the end. But we'll just do the simple flow around the sphere, and in your homework you'll have more opportunity to practice deriving the flows. Okay. Again, usually what you do is you have your objects, you try to derive your potential. Either you start from the potential and you add them up, or you start from the velocity field, that's the same, and you add them up. You apply your boundary conditions, and once you have your flow, you know that you can get to the pressure from Bernoulli. And that's a very strong form of Bernoulli, where the constant is completely independent on the streamliner. And so from there, then you can compute forces and drags and lift if there is any drag and lift. So here is our coordinate system. We're tilting everything. So Z, which usually is pointing upwards now, is our axis of axisymmetry. So we will be pointing towards the right. And then X is pointing inside of the board. And Y is pointing upwards. And the angle theta is the angle from the Z direction. Okay. So if I have a point here, this point is at a distance r from the origin, and that's the radial distance to the origin. It has an angle theta with the z direction, but then if you project it, it's not necessarily in the zy plane. It could be anywhere in the xy plane once you project it. Right. And this angle here is the angle phi. And we're assuming everything to be independent on phi. So our axis of axisymmetry is z, and therefore the flow is never, we don't have a flow in the circumferential direction. Okay? Is that geometry clear? And our sphere is going to be centered. So this is our coordinate system. I'm not going to reproduce where the coordinate system and the sphere, otherwise it's going to be confusing. But our sphere is going to be here. And the flow the uniform flow at infinity is going to be in the x direction. So this, we're going to look at the flow around this object. Okay. Now, because everything is axisymmetric, it doesn't really matter what phi is. It doesn't really matter what x, y, x is y. It doesn't really matter what phi is. It doesn't really matter what. So we'll take phi equals to 0, and I'll project everything in the xz plane. Right, so in the xz plane, then the problem that we have is the following. This is x z plane, and then the sphere is just that circle here, and then the angle theta is this angle here. Okay, so it looks like a cylinder, but it's not, and that is our uniform flow. So what singularity do you think you will need in order to represent and to impose the right boundary condition for the flow around the sphere? Now, if you followed what we did for cylinders, you would say a uniform flow and a dipole. Okay, and this is exactly what we need. We don't have irrotational vortices again, so those are the two things that we will need. So we will write our potential. The potential can be written as a superimposing of a dipole, a uniform flow, I should say. Uniform flow and a dipole. So we'll write our potential, phi. This is our velocity potential at any point x. Now note that at point x is going to be determined by the distance to the origin and by the angle from the z axis, from the z, yeah. So it's no longer x and y, and we're really looking in spherical coordinates. And we'll superpose a uniform flow. Now, in spherical coordinates, a uniform flow has a potential u r cosine theta. And you can refer you back to your book. So those formulas, we'll put them in a cheat sheet for an exam. But they will all be there, or they will be given to you. This is not something which I really expect you to learn by heart. Plus a dipole, and a dipole of strength d has a potential of d divided by 4 pi r squared cosine theta. So this is the potential associated to a velocity field where you have a uniform flow and a dipole at the origin. So this here is our dipole, this here is our uniform flow. And this here is a dipole at the origin. Now, how do we make sure that we impose the right boundary condition, that we have the flow around a sphere? Well, we simply need to impose the no penetration boundary condition at the surface of the sphere. Right? Remember, we are in the realm of ideal flows. So the flow derives from potential, the flow is irrotational. When a flow is irrotational, you know that the Laplacian of the velocity is equal to 0, and therefore the flow is inviscid. And there are no effects there are actually no, the flow geometry doesn't allow viscosity to actually act on the flow. So the flow is completely inviscid, and therefore you cannot impose a no-slip boundary condition. Right? You can only impose a no-slip boundary condition when you have a viscous flow. So here we cannot impose the no-slip boundary condition, so we have to impose a no penetration boundary condition at the surface of the sphere. That is to say, at the surface of the sphere, u, therefore at r equals, I forgot to give a name to the radius of the sphere, so I'll give it the name a. Put that here. This is our sphere. The radius is a. Okay. So u, the velocity field at r equals a, and for any theta dotted with the normal vector at the surface of the sphere has to be equal to the velocity of the sphere projected in the normal direction, but here we're assuming the sphere is not moving. Right? Therefore, this is going to be equal to 0. Yeah? This is equal to 0. So how do I get to that? Well, we need to get to the velocity field. The velocity field in ideal flows is the gradient of the potential, by definition of the velocity potential. So we have to compute the gradient of the potential, and we are in spherical coordinates. So our gradient, so let me just write in a coordinate system. So UR, which is the velocity in the radial direction, is partial phi partial r, and U theta, which is the velocity, hold on. So here, at any point at the surface of the sphere, r is my unit vector pointing in the radial direction, and theta is this unit vector pointing in this direction, right, in the positive theta, so it's going upwards here. So in the r direction, the component of my velocity field is partial phi over partial r, and in the theta direction is 1 over r partial phi over partial theta, right? Now I could compute the two components, but you know that the normal vector to the surface, at the surface of the sphere, is going to be the unit vector in the radial direction. So at the surface of the sphere, this normal vector to the surface is r. Okay? And so u dot n is just the r component, the radial component of the velocity field. So I'm just going to compute ur, and ur is going to be partial phi over partial r. So I have to differentiate those two components here. So when I take partial phi over partial r of this, I get u cosine theta. This is equal to u cosine theta. And when I take partial phi over partial r, so the derivative with respect to r, the derivative with respect to r of this term here is minus 2d divided by 3 times 4 pi r cubed cosine theta. Okay, so I get minus 2 divided by 4 pi, I have a d r cubed cosine theta. Okay, and u theta, you could compute it, but it's not necessary, so I will just not compute it. So again, my radial component, once you simplify, is u cosine theta minus d divided by 2 pi a cubed times cosine theta. And when we impose our boundary condition, we have to impose that ur at r equals a, and again for any given theta is equal to 0. So this is u, or you can factorize the cosine theta. So cosine theta u minus d divided by 2 pi. Sorry, I put an a, but that should be an r. Here, I haven't. This is ur in the general case. I'm not saying that I'm r equals a. I'm not saying I'm at the surface of the sphere quite yet. So when I am at the surface of the sphere, this becomes minus d divided by 2 pi a cubed, 2 pi a cubed. And this needs to be equal to 0. Therefore, you can identify the value of your dipole. And so d is going to be equal to 2 pi a cubed times u. Yeah. And so this is the flow around your sphere. So if you write the potential phi for the flow around the sphere, it will be u r cosine theta plus 2 pi a cubed u divided by 4 pi, so this is 1/2 r squared, let me get rid of that, cosine theta. And the dimensions are correct. I have u and I have the dimensions of velocity times dimensions of length, so everything is looking good. This is the potential associated with the flow around the cylinder, around the sphere, sorry. Flow around a sphere. Now note that really this is a sphere at rest. The sphere is not moving, and the flow at infinity is equal to u in the x direction. And so this is a wind tunnel type setting. The profile or the object is not moving, and we have a non-zero flow at infinity. Okay, it's the same sort of configuration that we had for the flow around the cylinder. Okay, so you see this is exactly the same methodology as what you would use for 2D planar flow. So whenever you're facing a problem, always make sure that you get the right formula for the right. This is just a formula thing. You have the right formula associated with the right geometry. So if the flow is a 2D planar flow, you can use either complex potential, or you use the potentials for with the formulas for a 2D planar flow. And if you have a 3D axisymmetric flow, you use the potentials associated with 3D axisymmetric flows. Yeah, don't get the two mixed. Is that okay? Okay, so here I impose directly the velocity, the boundary condition. Yes. Oh, you're right. Yes, absolutely. Thank you. It's always a problem. Now my z is pointing in the x direction, so I get those confused. But you're right. This is in the z direction. How else could you have imposed the boundary condition, the no penetration boundary condition? It's the same as for 2D planar flows with the stream function. Right? You could have also, you have all the expression for the stream function, so let me do that real quick, or you could check, let's do a simple check that, let's check that the sphere is a streamline. Right? You could have directly checked that with the stream function. So when you do the same thing with the stream function, well, the stream function associated with a uniform flow and a dipole, you just go back to the formulas, they are in your book again. For a uniform flow, the stream function is 1/2 of u r squared sine squared theta. This is for a uniform flow. This is the stream function for a uniform flow. And then you add the dipole plus the dipole, which is d divided by 4 pi times r times sine squared theta. This here is for the stream function for a dipole, right? And you would want, of course, the sphere, the surface of the sphere, so this is represented by r equals to a constant a, to be a constant. Right? So let's look at what the stream function at r equals a and at any given theta is equal to 1/2 u a squared plus d 4 pi a times sine square of theta. And if we want this to be a constant regardless of theta, right, this is always going to be a function of theta. The sine squared theta is always going to vary with theta, so we need this constant here to be equal to 0. So that needs to be equal to 0. In principle, it gives you the same value, but it Doesn't. I have a minus sign floating. So I think I got the stream function wrong. The stream function here has a minus sign. So hold on, let me just change that. Actually, the stream function here has a minus sign, which doesn't show in my notes. But you should have a minus sign here, and therefore a minus sign there. And you see that you have, if this is to be a constant, that means that this is never going to be a constant. This is always going to be oscillate. It will always vary with theta. So we need this to be equal to 0, and that gives that d will be equal to, again, 2 times u times aq times 2 pi, so which is what we had before. Is that clear? Yeah? You know, another question might be, you know, are there stagnation points as the surface of the sphere? Now, you've seen a few of these flows now. Do you think there are stagnation points at the surface of the sphere? What do you think? Yes, how many? See two people nodding there. How many stagnation points? What would you think? 2. One in the front, one in the back. Right now, how would you answer the question if you actually wanted now to show that there are indeed 2 stagnation points? Yeah. Right. So you go back to this here. At the surface of the sphere, you already impose that ur was equals to 0, right? And so you compute u theta, and you look where is u theta equals to 0. And in principle, you would expect u theta to be equal to 0 at theta equals 0 and at theta equals pi. And I will give you the 2 stagnation points. Yeah. If you wanted to compute the force onto that sphere, what would you do? Yeah. Yeah. Exactly. So you while you differentiate the velocity, you have the velocity field. Now you get to the pressure with Bernoulli, right? And then you integrate the pressure with the entire surface. Now, what do you think you'll get? 0. Okay. There is no drag. It's the same D'Alembert paradox, because you're in viscid flows. You do have higher pressure on the front, but because there is no separation in ideal flows, then you also have a high pressure at the back. And so those 2 high pressure cancel each other, and in the end, there is no net drag onto a sphere. So I think as an exercise, it would be extremely good that you compute the drag force. So I'm not going to do it here, but this is to do. You want to do the stagnation points at the surface of the sphere. And you want to do compute the drag force. Now the procedure is the same as what we had before, right? You know phi. If you compute the gradient, you know the velocity field u. If you use Bernoulli, you know what the pressure is. Now you identify the constant in Bernoulli at infinity, right? And then you simply write that the drag is going to be the surface integral. So that will be from theta equals 0 to pi, and from phi equals 0 to 2 pi. Except you expect nothing to depend on phi, so that's going to be a 2 pi factor, times your pressure, minus the pressure on your normal vector n, but your normal vector is just a radial vector. So let me write directly r, times your surface, so this is a d theta, a sine theta, d phi. This is your element, this is your ds. This is your element of surface ds. Now at this point, just like what we did before, for whenever we're doing a momentum balance, it's always very important. It will simplify your algebra if you already know, a force is a vector, and here you're only interested in the force in a particular direction. So instead of computing the 2 components of the force, the x and the y, you just directly project this onto the z. Okay, and then you only focus on the drive. All right. Actually, in your midterm, a lot of you made that mistake. There was just half of you. When you do a mass balance, then of course you look at all, where the mass coming in and out. When you're doing momentum balance, a momentum equation at the control volume is a vector equality. One component is, if you want, a force equilibrium in the x direction, and the other one is in the y direction. Right? So you don't count the same way momentum which is coming in the x direction and momentum which is coming out in the y direction. Always projected either on the x or the y direction, depending on which one is most useful. Huh? So forces are vectors. When you write a vector identity, you have two directions. If I didn't project this on z, that would give me two components, one in the x direction, one in the z direction. I'm looking at the drag, I'm only looking at the z direction, so I dot it with z here. Yeah? Okay, good. So this is the flow around a sphere. And so there are many more examples of flow that you can do. And now the last thing, the second to last, if I have a little time, I'll show you a little bit of conformal maps. So we'll go back to 2D planar flows, but just briefly to show you how useful complex analysis can be. So the last part in ideal flows will be unsteady ideal flows. So if you remember from our very first lecture, the one where we derived the roadmap, I told you one of the goals also of IFD is to introduce all of the basic solution of fluid mechanics. Right? So everything that we see here, those are sort of very typical flows, the essentials, analytical solution that you need to know to understand the flow around more complex geometries. So the flow around the cylinder, you essentially need to understand that to understand airflow theory. The flow around the sphere, you'll need for flow around the sphere, but also, as we'll see here, to discuss added mass. So of course, whatever flows you will encounter in engineering will be around much more complex geometries. So the tools that we're using, those analytical tools, might not be, you may not be able to apply them directly, but the physics of the flow is going to be the same. So you really, if you understand those flows here, then you will understand flow around more complicated, in more complicated settings. Right? Now, one thing which we often assume, actually for ideal flows up to now, is that we had a steady flow. So if you just think about following a previous example of the flow around the sphere, what told you that you had a steady flow? What was the important component? Why did we have a steady flow? Huh? Exactly, right? Because the flow coming in from infinity was steady. It was not dependent on time. If the flow at infinity depended on time, then the flow would not be unsteady. Right? The flow would not be steady, it will be unsteady. Now, steady flows means that nothing changes with time. It doesn't mean that nothing. It does not mean that nothing moves. This is static. Right? Steady means that nothing changes with time. So if my boundary condition doesn't change with time, my sphere is at rest, and I have a constant incoming flow from infinity, then I have a steady flow. Okay? So now we'll discuss a very prototypical solution, example of unsteady flows, and that has to do with a flow where the object now is no longer at rest. Actually, even if it wasn't at rest, even if it was moving, my sphere, and let's put yourself now no longer in the frame of reference of the object. We're no longer in the wind tunnel, we are in a real life situation, and the object is moving. Right? If this object is moving at a constant velocity, right, then you can always argue that I can put myself back into the frame of reference moving with the object, and there everything is steady. And then you go back into a steady flow. Right? You see that? Now of course, if you are not in the frame of reference moving with the object, and the object is moving at a constant velocity, then the flow is unsteady. Right? Just think, if I have a ball just coming right in front of me, the ball is right here. Currently, I see nothing. and then the ball comes in, the flow is going to have to move around the ball, and then it's going to move back behind the ball. And this is unsteady. And my velocity was 0, now it's up, now it's this way, now it's back here, and now it's, when the ball is back there, again it's 0. This is a very unsteady situation. But if the velocity of the ball was constant, you could always go back into the reference frame moving with the ball, and then everything would be steady. Okay? Now you have an unsteady flow when that velocity is not constant. And the flow will be unsteady both in the frame of reference moving with the ball and in the frame of reference in the lab. So if the ball is now accelerating, of course if I'm in the lab, this is still very unsteady because it's accelerating now. No flow, no flow. This is unsteady. But also in the frame of reference moving with the ball, now my boundary condition at infinity is changing because the velocity at infinity is changing. Yeah? So that would be an unsteady flow. So we'll do that, and we'll just do one example, which is the example of a sphere, and that could be any sphere, now a sphere of aluminum, a sphere of iron, a soccer ball, anything which is accelerating, and accelerating means that the velocity is not constant. Right? So if the velocity increases, you accelerate, if the velocity decreases, you decelerate. Yeah? So let's take this example of a sphere of aluminum or a soccer ball or anything, right? Which accelerate in a fluid, and that could be air, or that could be water, or any of these. So at the very fundamental level, this is going to be very different. Right? So if I have a sphere, and say my sphere is moving at a constant velocity, so here u is constant, you know that you do not have a force in the z direction. Right? There is no drag. If u is constant, there is no drag. F is equal to 0. Okay? Now, if u is not constant, then you will have a force in the z direction. So u here is a function of t. There is a force in the z direction, even for inviscid flows. Okay? Now this force will not be called a drag force. This force is called the added mass force, or usually just the added mass. Okay? This is how it will be called. And so we'll be discussing added mass, and in principle, in a few minutes, you will understand why this is called an added mass. Now, before we start digging into where does that force now come from, and why do we have a force when the velocity is a function of time, if I ask you to compute the force exerted by the airflow or the water flow onto the sphere, which equation would you write? What is that force? Huh? Yes, so this is when you write in Newton's second law. And if you had access, yeah, but now I'm asking you to directly compute the force. So you're using a law that allows you to link the force with the velocity which you observed. Right? But Just the, well, it would be just, it would, actually no. Well, yes and no. So what do you call the drag force? What term of the Navier-Stokes equation, or what term do you integrate? Huh? Those are surface forces. Yeah, the only thing, the action of the air or the water onto the ball is a surface force. Right. So that force would be the integral over the surface of the sphere of what? Yeah, the pressure due to the flow in general. Huh? It could be unsteady or not steady, but so minus P times N ds. Yeah? Do we agree on that? Okay. So now don't write this, but I have another question for you. So assume now that you have how am I going to do that? So say this is a ball. Again, it's a ball of, let's say it's a ball of plastic with air inside, and it's in water, right? So it's negatively buoyant. It's less dense than water. Okay, and this is in water. What is going to happen to that ball? It's going to rise to the surface. Yeah. Okay. So it's going to rise. It's going to rise to the surface. Now, usually, if you were to compute the forces onto this object, right, what forces do you have? You have the buoyancy force, which is what? Huh? The displaced volume, so there will be 4/3 of P pi a cubed, yeah, this is the displaced volume.
Then the water density.
That water density. So the buoyancy is not minus the density of the sphere. Right? The buoyancy force is just the displaced volume. Right?
Oh, okay.
Yeah. So this will be this times g in the positive z direction. Yeah, and then you will have the weight. Right. So you don't have to note that. Right? This is the density of the ball, the average density of the ball, times g, z. Now, is any of these a fluid forces? Like what kind of force is that? Where is this applied? If you were to split, is one a bulk force, or these bulk forces, or these surface forces? Say you take a control volume, which is exactly just your ball, so there's almost no fluid around. Right, and you write whatever we wrote before. Right, before we were writing, if you write your control volume, then you write triple d over dt of rho u dv equals minus rho u dot n ds plus double integral of your surface forces plus double integral of your body forces, right? This is our control volume, except now there is no more liquid inside. Now let me ask you, where is this force? In this equation here, it's the body force, it's there, yeah. Now where is this force? Huh? Surface forces. Yeah? Is that clear to all of you? This here is really in there. It's the integral of the hydrostatic pressure. Right? So if you just had water, then this T here will be just minus P N ds, and if everything is hydrostatic, let's say, right, then P, remember that you just have minus dP dz equals to minus rho g, and you get a hydrostatic pressure. It's just because you have a hydrostatic pressure that you have this buoyancy force. But this buoyancy force is not a body force. This is part of your pressure force. The only term, right, the only force that the fluid exerts onto your sphere, if the flow is ideal, is this one here. Right? So in this force here includes the buoyancy force. Is that clear to all of you? Yeah? once you integrate the pressure, so we're in inviscid flow, so there's the viscous part is not there. So once you integrate the pressure force along the surface of your object, then you have the total force exerted by the water, by the liquid phase, onto your object. Right? And the buoyancy force is part of that. Now, I'm just making this clear because in a second we'll just see another term which will come in just the same way, which is the added mass term. Okay, so this is our force. Now, if the flow is unsteady, what simplification of the Euler equation are we going to use? So we have an ideal flow, so the flow is incompressible, and the flow is irrotational, that's the important part. And now the flow is unsteady. So you could write Euler's equation, of course. So you could write, well, let's solve this. And this. Right, those are your Euler's equation. But if the flow is irrotational, what equation are we going to use instead? Which is a simplification of this equation. Unsteady Bernoulli equation. Okay? Because unsteady Bernoulli equation is valid for incompressible flows, and still valid if the flow is not steady, so it's unsteady. So we use so this simplifies for irrotational flows. To the unsteady Bernoulli equation, which is rho d phi, rho d phi dt plus p plus 1/2 rho times the magnitude of the flow velocity squared, plus I'm going to assume that the only body force that we have is the body force inside of the fluid is gravity, so there will be rho g z, and that is equal to a constant. Again, this constant does not depend on the streamline. For irrotational flow, this is a constant everywhere. So this constant has dimensions of p, so let me call it p atmospheric. For instance, if the flow was 0 at infinity, you would identify this constant at infinity, so this would be equal to 0. And this might be equal to 0 at infinity, and this will be just p at infinity. So this constant, always identify this constant where you know all of the other terms. There might be one point in the flow, and you don't have to follow a streamline. There might be one point in the flow where you can identify all of these. That's the point where you want to identify a constant. Okay, so in this frame of reference, let me just then extract P, because this is what we want. We have pressure, and the pressure will be equal to 1/2, well, it will be equal to a constant, plus 1/2 rho times the velocity squared, the normal velocity squared, plus rho gz minus rho partial phi over partial t. So if I have an unsteady flow, and I know the flow, if I know the flow, I know u, I know the velocity, I know the potential, therefore, and I know the time derivative of the potential. So I know this term, I know that term, I can compute the pressure. Right? And from this, then I can get to the total force. And so the force, F, is going to be equal to the double integral over the surface of my pressure, right, minus P and ds. So this is equal to the double integral over the surface of, I'll put the minus sign outside, the constant plus 1/2 rho u squared plus rho gz minus rho partial phi over partial t onto n ds. So this is my force. Yeah? Do we all agree on that? Yeah. So now I'm going to resplit. When you integrate a constant times mds over a closed surface, what do you get? 0. Right? It's just like, if I'm thinking about this little object in the bowl, the pressure doesn't impose a net force onto that object, because pressure pushes on all sides of my little ruler, and therefore all of the contribution to pressure, I do have pressure pushing here on that surface, I do have pressure pushing here on that surface, but they cancel. That's just what you have when you have an isotropic pressure. So integrating the constant is not going to give me anything. Oh yes, of course, yeah. Sorry about that. I have minuses here. Minuses here. They're all, yeah, constant. Okay. Okay, so here, let me write that. So this here is going to be equal to 0. Now what do you get? And this we did many times. When you integrate that part here, when you integrate around the surface of this around the surface of your object, 1/2 of rho u squared. What do you get? How have we called this part? The drag. Right? This is what we computed before. This is the drag. This here is really this is the static pressure, and you're integrating the static pressure along your profile. This is really, if you decompose in different components, this is what we call the drag. Now, in our case of inviscid potential flows, what is that term going to be equal to? 0. And here, I should say, this will be the drag / lift. Right? So for a 3-dimensional flow, it will always be 0, both in the z and the x direction. For a 2D planar flow, it will be 0 in the x direction, so there will be no drag. There could be a lift if you had an irrotational vortex. Yeah? So this is the drag / lift, depending on which direction I project this f. Okay? So here, if I project it on the z direction, I get 0, both for a 2D planar flow and an axisymmetric flow. But if I project it on the direction perpendicular to my incoming flow, then for 3D axisymmetric flows, I still get 0. We discussed that, just like for a sphere. But for a 2D planar flow, like the flow around the cylinder, if I did have circulation, then I would have a non-zero lift. Yeah? So this is drag lift. Now what is this term here? Yeah, so we just discussed that. So how do you call that force here? That's the buoyancy force. Right? So the buoyancy force is always hidden inside of your pressure. The buoyancy force is going to come in if you have a heavy fluid, for instance, and the hydrostatic pressure varies over the scale of your object. So this here is the buoyancy force. So buoyancy is always a terrible word to write. I always get the spelling wrong. This is your buoyancy force. Right? And then this one you've never seen before. Right? This is a new force. And you see that you only have this component here if you have an unsteady flow. Only if your potential changes with time. If your potential changes in time, that means that your velocity changes in time. So only if your flow velocity field changes in time do you have that term. And this term is the added mass term. Okay? So this is what you call the added mass. Now you'll see, we won't do the whole derivation, we'll just do part of it after the break. But you'll see that you have a dphi over dt, so that looks like a du over dt, and you'll see that then this force is going to look like if your ball was a bit heavier. Right? So we'll discuss that in a second after the break.